Okay, so today we're going to be doing some more complicated calculations with latent heat. In the PowerPoint slide, we're on slide 67. This is example 3. Okay, so just to recap, remember last class, or during the last video, we talked about the idea of latent heat having to do with the energy required to phase change 1 kilogram of a substance. If you're melting or freezing, you're dealing with the latent heat of fusion. And if you're talking about boiling or condensing, you're dealing with the latent heat of vaporization. And the equation involved looks like Q equals mL. Okay, so that's when you have a phase change, as opposed to when you have a temperature change, where you have MC delta T, which has to do with specific heat capacity. Okay, so that's when you have a temperature change. And it's definitely possible to have both in a problem, and so that's what we're going to see in these next few examples. So example 3 says the boiling temperature of water is 100 degrees Celsius, and the latent heat of vaporization for water is 2.3 times 10 to the 6 joules per kilogram. The specific heat capacity of water is about 4,200 joules per kilogram per Kelvin, and the specific heat capacity of steam is about 2020 joules per kilogram per Kelvin. First question is just a concept question. Which takes more energy, boiling 2 kilograms of water at 100 degrees Celsius or boiling 2 kilograms of water at 90 degrees Celsius? Now, right off the bat, I'll tell you the correct answer is the second one. And the reason it's the second one is because if we want to boil 2 kilograms of water, to calculate the heat required, we would just do Q equals M times L. And the reason is the water, the boiling point of water is 100 degrees Celsius. And so if we have water that's already at the boiling point, when we add heat, the first thing that's going to happen is that the water is going to boil. All that heat that we're adding is going to go to increasing the internal potential energy of those water molecules, which is going to result in a phase change, but not a temperature change. Okay, and so this is the only equation that would apply in this situation. Whereas to boil 2 kilograms of water at 90 degrees Celsius, well, the thing is that water, under normal conditions, does not boil at 90 degrees Celsius. And so when we add heat to the water that we want to boil, the first thing that's going to happen is, well, it's not going to boil right away. First, we have to increase the temperature of the water from 90 degrees up to 100 degrees Celsius, which is the boiling point of water. And so first we have to add in a little bit of heat to cause a temperature change. Okay, and so that's going to be given by MC delta T. And then once we add in this amount of heat to heat up the water to 100 degrees Celsius, then we also have to tack on the heat required for the phase change. Okay, and so it takes more heat to boil 2 kilograms of water at 90 degrees Celsius just because we have to add a little bit of extra energy in there just to get it to the boiling point. Okay, so that's kind of a concept question, but you can kind of see how these two equations relate with each other. Now let's do some calculations. How much heat would be required to boil 2 kilograms of water at 100 degrees Celsius? Well, we already know that's given by Q equals mL. And so Q equals mL, that would be the mass is 2 of the water. And because we're boiling, we want to use the latent heat of vaporization, which is 2.3 times 10 to the 6. And so that would be 4.6 times 10 to the 6 joules, or 4.6, wow, it's a J. 4.6 megajoules, if you want. Again, that's a J. Now for the second question, how much heat would be required to boil 2 kilograms of water at 90 degrees Celsius? We have to add on the little extra amount required for the temperature change. That would be MC delta T plus mL. And so it would be this 4.6 times 10 to the 6 joules plus this little bit required for the temperature change. So that would be 2 times. Now, if you look at the problem, we're given two specific heat capacities. So you have to ask yourself, which one should I use? Well, we're dealing with water right now. We want to temperature change the water, and so we need to use the specific heat capacity of water, which is 4,200. And then delta T, the final temperature minus the initial temperature. Remember, delta T can be in Celsius or in Kelvin, would be 100 minus 90, which is 10. and then we have to add on that 4.6 times 10 to the 6 that we had before. Okay, and so I'm just going to type this into my calculator. That would be 2 times 4200 times 10. That would be 8.4 times 10 to the 4 plus 4.6 times 10 to the 6. And if you add those two things together, you should get, sorry, that should be an equal sign, equals 4.684 times 10 to the 6 joules. So that is the answer to the second question. So that's for the first question, that's for the second question. And the last question for example 3 says, how much heat would be required to heat 4 kilograms liquid water from its melting point until it turns into 150 degrees Celsius steam? So this is going to take a little bit more space than I have right now. So pause it here if you need to finish writing this stuff down. I'm going to clear the screen and then I'm going to go to another slide or another screen to do this last calculation for example 3. Okay, so I'm going to clear this off. And I'm going to go over here to do this problem. So this is going to be example 3, okay, part C, if you will. And so we want to know how much heat it takes to heat 4 kilograms liquid water from its melting point until it turns into 150 degrees Celsius steam. Okay, so first of all, the melting point of water is what? 0 degrees Celsius. Okay, so that means we start with 4 kilograms of water at 0 degrees Celsius. Now, if you don't know the melting point of water, there's no way you can answer this question. Okay, so that's definitely something you need to know. Now, when we add heat, remember there's only two places the heat can go, because either way the internal energy of the water has to increase if we're adding heat to it. Either that energy goes to increasing the kinetic energy of the molecules, which is going to increase the temperature, or it goes to the internal potential energy of the molecules, which is going to cause a phase change. Okay, now, as we add heat to water that's already been melting, it's not going to phase change the water because the water is not going to phase change again until it reaches its boiling point at 100 degrees Celsius. Okay, so we want to find what Q is, and the first thing we're going to do is we need to get to that boiling point. Okay, so we're going to have a temperature change from 0 degrees Celsius to the boiling point of water, which is 100 degrees Celsius. Now, it would be different if this was 4 kilograms of ice, and we had to phase change the ice at first, but in this case the ice is already melted, it's water, it's just very cold water. Okay, so the first thing we're going to do is we're going to add enough heat into temperature change up to from 0 to 100 degrees Celsius. Okay, then once we get to 100 degrees Celsius, as we add in more heat, guess what's going to happen? It's going to cause a phase change. Okay, now the heat required for the phase change is given by m times L. Okay, the mass times the latent heat, specifically the latent heat of vaporization, because we're talking about steam. Now, once we've phase changed all the steam, remember during this part, if you think back to the graph we saw in the last video, the temperature is not changing at all. So all the heat we're adding during this stage is just going to the phase change. Once we're finished with this phase change, what do we have left? We have 4 kilograms of steam sitting at 100 degrees Celsius. Okay, so this whole time it's staying at 100 degrees Celsius. Well, we want to end up with steam at, I believe, 125 degrees Celsius. And so the last step is we're going to do another MC delta T, and we're going to temperature change the steam now up to 125 degrees Celsius. Okay, so you always do these heat problems in stages. Okay, so the mass is 4. Remember in the first segment, the thing that we're temperature changing is water, which has a specific heat capacity of 4200, and delta T of the water, it's going from 0 to 100 degrees Celsius, is going to be 100 minus 0, which is obviously just 100. This right here is going to be 4 times the latent heat of vaporization, which is given in the problem. And then for this segment over here, again, you have to think and keep in mind, what is it that we are temperature changing? Well, once we get past this stage, we're no longer dealing with water, we're dealing with steam. And so that would be the mass is still 4, but now we have to use the specific heat capacity of steam, which is given in the problem as 2020. Okay. Now, what is delta T? This is why you break down the problem like this. Delta T is 125, which is the final temperature of the steam, minus 100 degrees, which is the initial temperature of the steam. A very big common mistake is to simplify this problem and be like, oh, the initial temperature is 0 and the final temperature is 125. But you can't do it that way because part of the time it's water and part of the time it's steam. So you have to do it in segments. If you're using the specific heat capacity of steam, which is 2020, you can only use that so long as you're dealing with steam. And you're only dealing with steam from 100 degrees Celsius onward. Okay, so you have to do it in stages like this. So from now, all we have to do is plug all this stuff into the calculator. Okay, so I'm just going to do that. I get 1.68 times 10 to the 6 plus 4 times 2.3 times 10 to the 6. That's 9.2 times 10 to the 6 plus 4 times 2020 times 25, which is 2.05 times 10 to the 5. And so we end up at the final answer. We add all this up into our calculators. Okay, let me just do that. And the answer I got is 1.11, I rounded a little bit, times 10 to the 7 joules. Okay, so this is the answer to the last question for example 3, and that should give you a pretty good idea of how complicated these problems can get. Okay, so remember you have to do these in stages. Either you're doing a temperature change or you're doing a phase change. You cannot have both at the same time. Okay, so pause there for a second if you need to finish adding that to your notes, and then we'll go on to the next example. Okay, so just to clear the screen, let's go back to the notes. Example 4, it says the boiling temperature of water is 100 degrees Celsius, the latent heat of vaporization for water. So all these values are basically the same as what was given before. How much heat would be released by condensing 2 kilograms of water at 100 degrees Celsius? Okay, now remember, heat that's being released is typically thought of as a negative value. If we're condensing, that's the opposite of vaporization, so we should be using the latent heat of vaporization. This is actually a very basic calculation. Okay, if we have 2 kilograms of water that's already at the point of condensation, right, we don't have to temperature change it at all. All we have to do is directly plug into the equation and it will be done. Okay, so that would be 2 times 2.3 times 10 to the 6. Now do keep in mind, you have to be very careful with this. This equation for latent heat is not smart enough to know whether it should be positive or negative. Okay, it's not like the MC delta T equation, which can give you a negative answer. And so if you know it's supposed to be negative because heat is being released, that means Q should be negative, you have to go on and add the negative on your own. Okay, so that is example 4. Okay, for the first part. The second question says, how much heat would be required to heat 4 kilograms of liquid water from its melting point until it turns... Hey, wait a second. We already did this question before. Okay, I'm not doing that one again. Okay, so we are finished with example 4. Pause it there if you need to look over that. Okay, and then finally, example 5. This is a little more of an involved problem, and so we're going to go to another screen to work this out. But before we do that, let's identify our variables. Now this is kind of interesting. It says how long. Right off the bat, this is different from the last couple of questions, because how long is a question about time. So you might ask yourself, well, how does time play into this? If you look over here, though, we're given that the heater that's melting the ice has a power of 50 watts. Now remember that 1 watt is 1 joule per second, and so this is power based off of the units. So power is energy over time. Okay, and so that's going to be our connection here. Because we're given the power, we're trying to find the time, and the energy in this case is going to be thermal energy, or the transfer of thermal energy, which is heat, right, which is Q. Remember, heat is measured in joules. So how long will it take the heater to melt 2 kilograms of ice at negative 10 degrees Celsius? Okay, actually, I might try to work it out on the screen. Hopefully I have enough room. Now, we're going to start with finding our equation for Q, and then once we get Q, it should be very easy to find the time. Okay, so when you do this problem, you have to think, okay, I'm adding the heat to the ice. What's the first thing that's going to happen to the ice? Does ice melt at negative 10 degrees Celsius? No. Ice melts at 0 degrees Celsius. Okay, so what is the first thing that's going to happen when you add heat to this ice? The internal energy is going to increase, but all that energy is going to go to the kinetic energy of the water molecules, or the ice molecules, whatever, instead of the potential energy, and so there's going to be a temperature change, right? Because you can only have a phase change at the specific melting point. So the first thing that's going to be required is to temperature change the ice from negative 10 to 0 degrees Celsius. Then, once it reaches 0 degrees Celsius, you have to phase change the ice. Okay, that's going to require the latent heat of fusion. And let's see, is that all we want to happen? Just to melt the ice? Yes. Okay, so Q is just going to consist of these two terms. We're given the mass, we're given the specific heat capacity. Notice we have to use the specific heat capacity of ice, because while this temperature change is happening right here, from negative 10 degrees Celsius to 0 degrees Celsius, it's ice and not water. Delta T is just going to be 10 degrees, because it's going from negative 10 to 0. And then we have the mass times the latent heat of fusion. Again, notice it's the latent heat of fusion and not vaporization, because we're dealing with the melting point and not the point of vaporization. So if we take these two numbers and we add them together, I'm going to do 2 times 2108 times 10. I get 4.22 times 10 to the 4 plus 2 times 335,000. That is 6.7 times 10 to the 5. And I did round my first answer just a little bit in case you're wondering. And the answer that you should get is 7.12 times 10 to the 5 joules. And that's going to be our Q. Now that doesn't answer the question because we're still needing to solve for time. So if we know power is energy over time, we have P is 50 watts. That would be equal to 7.12 times 10 to the 5 joules. It's a 5. Divided by T. And so T would be equal to 7.12 times 10 to the 5 over 50. If you just rearrange with a little bit of algebra, divide by 50. Then I'm going to finish this up here. T should be equal to, again, your answer might be slightly different depending on how you rounded. That's fine, that's not a big deal. 1.242 times 10 to the 4 seconds. Which, by the way, if you think that's a long time, it is. Then again, it's a very weak heater, and you're trying to melt a pretty good amount of ice. Okay, so this is the example, or the answer to example 5. Now, as far as problems go involving heat and latent heat and specific heat capacity, this is generally about as difficult as you might see. I could maybe think of harder problems, but between example 3 and 4 and 5, hopefully you've seen a good range of problems. You're able to answer all the problems on your worksheet. Theoretically, people tend to do very well on these type of problems because they're not hard as long as you understand the concept. Okay, as long as you go in stages and make sure that you understand when to temperature change and when to phase change and how to combine all of those things. Okay, so just keep the principles in mind. You can only phase change at specific temperatures. As you add heat, either there's a phase change or there's a temperature change. You can't have both at the same time. And keep in mind that you're careful with the final temperature and the initial temperature, because you can only set the final temperature and the initial temperature as long as there's not a phase change in between. Okay, so hopefully you can use these examples here to finish working on your worksheet problems. Let me know if you have any questions.